All right, today we're diving into one of the most powerful and honestly one of the coolest algorithms in all of machine learning, the random forest. We're going to see how it takes a bunch of simple, even flawed models and combines them into something that is just incredibly accurate.
And this brings up a really fascinating question, right? It's the whole point of what we're talking about today. How can a committee where every single member has its flaws come together to make a decision that's nearly perfect? It sounds like a total paradox, but it's the secret sauce behind why random forests work so well. So let's pull back the curtain and see how it's done.
So here's our game plan. First, we'll start with the basic building block, what I like to call the overfitting genius tree. Then we'll look at how you assemble a whole team of these trees using a method called bagging. After that, we add the magic ingredient, randomness. Then we'll see this whole thing in action with a real-world example. And finally, we'll peek inside to see what the forest can actually teach us.
Okay, first up, the genius tree. We're about to find out why a single expert, even one that seems brilliant on the surface, can actually be super fragile and, frankly, not very trustworthy.
You see, the foundation of a random forest is something called a decision tree. You can just picture it as a big flowchart of yes or no questions that a computer learns from looking at data. And it can get crazy good at predicting things based on the data it's already seen. But that's the problem. It's too good. It doesn't learn the rules, it just memorizes the answers. We call this overfitting, and it means the moment it sees brand new data, it totally falls apart.
And there's a technical name for this problem: high variance. It just means the model is really unstable. If you just change one or two little data points in what you feed it, the entire structure of the tree can change completely. And that, right there, is why you can't rely on a single tree to make predictions on its own. It's just too twitchy. So, if one tree is unreliable, what do? Well, you build a committee, of course, and that brings us to our next big idea, assembling a team using a technique called bagging. The whole point is to average out all those individual mistakes. Now this process, which is called bagging, is pretty clever. You start with your original pile of data. Then you create a bunch of new, smaller data sets by just randomly picking data points from the original, but here's the trick: you do it with replacement. That just means you can pick the same data point more than once. So you end up with all these slightly different data sets. You train one unique decision tree on each one, and when it's time to make a prediction, they all just vote. Majority rules. Simple as that.
Now here's a really cool side effect of this whole sampling method. Because we're picking with replacement, on average, each one of those little data sets leaves out about 37% of the original data. This leftover data is called the out-of-bag sample. And this is just one of the algorithm's brilliant little tricks, because this OOB data acts as a totally free built-in test to see how well your model is performing. You don't even have to set extra data aside.
So what this all boils down to is that by averaging out all these different predictions, bagging smooths out that instability we were talking about. It cuts down on that high variance and makes the whole model way more reliable. And, this is the best part, it does it without making the model fundamentally less accurate. There's no trade-off. For unstable models like decision trees, it's just a straight-up, unambiguous win.
But there's still a catch. Bagging isn't perfect. It has this lingering issue you can think of as groupthink. See, if there's one really predictive piece of information in your data, pretty much every single tree is going to figure that out and latch onto it. And then they all start to look and act the same. They become correlated. And a committee full of clones isn't really any smarter than just one person, is it?
So, how do we break up this groupthink? Well, this is where the real genius of random forests kicks in. It's an innovation from a statistician named Leo Brayman, and he added one final, secret ingredient to the mix: a powerful dose of pure randomness.
And the solution he came up with is so simple it's almost hard to believe how powerful it is. In a normal bagged tree, whenever the model has to make a decision, it's allowed to look at all the possible features. But in a random forest, at every single one of those decision points, it's only allowed to see a small, random handful of the features.
So why on earth does this matter so much? Well, by hiding some of the features at every step, you force the trees to be different from each other. If that one super obvious, super strong feature isn't available in the random subset, well, the tree has no choice but to find other, more subtle patterns in the data to make its decision. This is what breaks the groupthink. It decorrelates the trees and creates a committee of genuinely diverse experts. And that makes the final vote so much wiser. Okay, enough theory. Let's see how this actually works in the real world. We're going to move from talking about individual trees to the power of the full forest. And we'll use the high-stakes world of credit risk to see what it can do.
A huge study back in 2015 tested dozens of different algorithms on credit scoring data, and, well, the results speak for themselves. A single decision tree, it scored about a 74% on a key accuracy metric. A classic standby model, logistic regression, got up to 79%. But the random forest, it blew them both out of the water with 89%. I mean, that is a massive jump in performance.
So why is it so much better? It all comes down to being robust. Messy real-world problems like complex relationships in the data, weird interactions between features, or just random outliers. These are all things a random forest just handles automatically. For an older model like logistic regression, every single one of those issues is a major headache that a data scientist has to go in and try to fix by hand. That makes it way more fragile.
But the story doesn't stop with getting a high score. One of the greatest things about random forests is that they aren't a complete mystery or total black box. For our last section, let's see how we can actually look inside the forest and understand what's driving its amazing predictions.
We do this with a tool called feature importance. What it does is, the model basically calculates a score for every single piece of information you gave it, and that score tells you how much that feature helped the forest make good predictions. The higher the score, the more important that feature was to the final outcome. It's that simple. And here is exactly what that forest saw in the credit risk data. The number one most important predictor of whether someone would default was their account status and their payment history. No surprise there. That was followed by how long the loan was for, how much it was, what they were using the money for, and finally, the applicant's age. This isn't just a prediction. This is real, actionable insight.
And that's really the crucial point to take away from all of this. Random forests give you this incredible 1-2 punch. You get state-of-the-art, best-in-class accuracy, and you get a clear look at the why behind the numbers. It's really the best of both worlds, top-tier performance and the ability to explain it.
So yeah, this wisdom of the crowd idea is incredibly powerful, but it's not perfect. It has one major limitation. A random forest is amazing at what's called interpolating, making predictions for things that fall within the range of data it's already seen. But what it absolutely cannot do is extrapolate. It can't predict a value that's higher than the highest value it was ever trained on. And that leaves us with a pretty critical question to think about. The forest is incredibly wise about the world it already knows, but how do we solve problems that require us to predict something truly new, something we've never seen before?